Hi, in the last module we talked about how to form MR images. In this module we're going to continue by talking about the concept of K-space. And this is a notational scheme that we use to kind of describe MRI data acquisition. So if you recall, we have this kind of two mathematical spaces. We have K-space and image space. So K-space represents the mathematical space where we make our measurements. So we choose different values of Kx and Ky, and in that way kind of transverse through K-space. And once we've acquired enough data points, we can apply the inverse Fourier transform and reconstruct the image in image space. So K-space is where the data is acquired, and image space is where the data is subsequently analyzed. Now, it's really important to note that there's not a one-to-one relationship between image and K-space. Each point in the image space depends really on all the points contained in K-space. So I can't choose a single point in K-space and expect that to give me full information about a single voxel in the brain. To really understand what a K-space measurement represents, it's instructive to look at it in one dimension as a time series. So let's look here and consider that we have take a linear combination of three different sinusoidal functions. So we have three functions here, 1, 2, and 3. Now, if we take a linear combination of them, we weight the first one by, say, 0.5, and the other one times 2, and the third one times 1. Then we're going to get a resulting function that looks like the one here on the bottom. Now, say I was given this particular function, and I was given the task of recreating which three sinusoidal functions went into making this function. It would seem like a difficult endeavor. However, if I take the Fourier transform of this function, I get the results here on the right. So I get three different spikes, and the spikes that I get are at different frequencies, and those frequencies are directly related to the periodicity of the sinusoidal functions that we had. The amplitude of the peaks in the Fourier domain are related to the amplitude of the curves that I used to make the linear combination. So for example, we see here the lowest frequency point has an amplitude of 0.5. This corresponds to the first curve, which has, since it has a low frequency, it has a long periodicity, because there's an inverse relationship between the two. And that particular function is weighted by 0.5. The next one is in between and is weighted by 2. And then finally we have the last one, which has very low frequency but high periodicity. And that one's weighted by 1. Now, K-space is really kind of the same thing. Here I have three different points of K-space. And for example, if I look at this first point, this green point here, if I have 0 everywhere in K-space except a 1 at that point, and I took the inverse Fourier transform, what I would get would be a kind of a sinusoidal wave floor like the one seen at the top right here. Now, the periodicity of this wave floor is related to how close to the center of K-space you are. So in this situation, I'm fairly close to the center of K-space, so these are low frequency areas, and so these are areas that represent high periodicity in the wave floor. So there's a long distance between the peaks of these waves. Now you'll also note that the direction of these waves is in the same direction as where the point is from the origin. Now if I move out to this tan point, you'll see that I'm moving in the same direction as before. So now we're looking at the middle figure here on the right. And as you'll see, the waves are going in the same direction because I'm moving in the same direction from the origin. However, the frequency is much higher, and so we're going to have a much lower periodicity, so we're going to oscillate much quicker. Now if we move over to the opposite side, to this red dot, now we're at the same distance from the origin, so we're going to have the same periodicity as for the tan dot, but now instead we're going to be going in a different direction because we're going from a different direction from the origin. So basically what we have in K-space is each point represents how much we should weigh a sinusoidal floor like this. And it's the linear combination of all these sinusoidal floors weighted by their K-space measurement that gives us the image. Now that's kind of hard to believe when you see this K-space. So basically these K-space measurements are weighing these sinusoidal floors, and what I'm claiming here is that the weights of these K-space measurements will give us this beautiful image. And that can be a little difficult to believe at first view. However, if we play around a little bit, let's say that we choose a point like this yellow dot here and just double the value of that K-space measurement. So by doing that, we're kind of disrupting the balance of the K-space measurements. If we do that and kind of place an artificial artifact there, the resulting Fourier transform will give us the following reconstruction. So now you'll see we have the same image as before, but it kind of looks like it's been pressed in a waffle iron. So we'll see that the wave floor going in the direction corresponding to that dot is overemphasized. And so this just destroys the fine balance in the image. Similarly, if we move the point over to the other direction, what's going to happen? Well, we're going to get a similar waffle type pattern, but it's going to go in the opposite direction since we're moving in the opposite direction, or we're moving in a different direction from the origin. This kind of illustrates that different K-space points mean different things. So K-space points towards the center have a very low frequency, so they represent waves that have a very long periodicity. And K-space points in the outskirts are high frequency and have a low periodicity, so they oscillate very strongly. Now, I'm going to do a little bit of an experiment. I'm going to take this K-space and I'm going to split it up into 9 equally sized boxes. So if I take the center box and set everything else equal to 0, and I reconstruct the image, I get the reconstruction to the right here. As you see, it still looks very much like a brain. It's somewhat blurrier than the previous brain that we had, but it's still, a fair approximation of what we had. You can, if you look closely, you can see the boundaries are not as sharp, and you can see a little bit of ringing in the brain. But this is usually only 1/9 of the K-space measurements, so about 11% of the K-space measurements. So using only 11%, we've lost relatively little. Now let's look at the remaining 89%, so the other 8/9. If we reconstruct the images using those 8/9, we get the following. So now these are only looking at K-space points that are far out, so that correspond to sinusoids that are highly oscillating. And so this is the type of information that we need in order to make out fine detail. And as you can see, we can see the skull very well, and kind of the boundaries between gray and white matter, and boundaries in general come up very well. Now, because the Fourier transform is a linear operation, these two images on the right hand side, they add up to the other image. So this is really kind of a decomposition into the image into two parts. And so we see that we have one which is kind of the contrast part, which is the center of K, which corresponds to the center of K-space, and we have a detail part which corresponds to the outer parts of K-space. So again, the information content says that the low spatial frequency represents parts of the object that change in a spatially slow manner, while the high spatial frequency represents small structures whose size is on the same order as the voxel size. So we can make out much of the contrast by just looking at the center of K-space, but if we want fine detail, we need to go further and further out into K-space. You can kind of see that when you look at the following plot. So this shows you different spatial resolutions of the same image. So let's say that we wanted to reconstruct a 32 by 32 image. Well, then we typically want to sample about 1,024 points in K-space, roughly. And then we would get an image like the one here to the top left. So this is kind of blurry, but you can kind of make out that it's a brain, but not much more than that. So if we want a better image, we might increase the resolution and look at a 64 by 64 image. So now the resulting image in the middle here looks much more like a brain. However, the cost has been that it now costs 4 times as much points in K-space to get that information. Finally, if we go to a 128 by 128 image, we can make out very fine detail in the brain. but now we have to sample, 16,000 points in K-space. So in order to make out this detail, we have to sample further and further in K-space in order to get these wave floors that can represent these fine boundaries. Okay, so that's the end of this module where we discuss K-space, which is a notational scheme which we use to describe MRI data acquisition. In the next module, we'll talk a little bit about fMRI data and go over some notation, and that's going to be the last module of this week. Okay, I'll see you then.